Okay, in this video we will be moving on to Chapter 17. And again, we had the first 4 chapters of the course where we looked at particles, and we looked at kinematics of particles, motion without regard to force. We looked at kinetics of particles, F equal ma. We looked at work and energy, and we looked at impulse momentum. That was the first 4 chapters where we focused on those topics for particles. Now we repeat those exact same topics in the exact same order, but now we're talking about rigid bodies rather than particles, or more complex bodies composed of interesting geometry, interesting shape. And what we learned in Chapter 16 was that rotation matters. And that's going to be the prime effect that we'll have to deal with in Chapter 17 as well. So Chapter 17 is planar kinetics of a rigid body. And key words are kinetics, meaning now we bring in forces. Rigid bodies, yes, but we're going to be dealing with planar kinetics, not general 3D kinetics. Okay? In order to deal with the idea of rotation, we will very quickly bring in the idea of the mass moment of inertia. The definition of the mass moment of inertia, and you've had this before in multiple physics classes probably, is that the mass moment of inertia is the integral of r squared dm. And so if we have a body of a given total mass, this is an indication of where the mass is located, or how far the mass is located from some center point. And the further out you put the mass, the greater the I value will be. And we will look at some examples of this in just a minute. I'll do the best I can on the video. So this dm thing, integrating over the entire mass of the body, we will then turn into a volume idea, because for the problems we'll be working, we'll be assuming that the mass is composed of material of the same density everywhere, and that density rho would be known. Therefore dm can be written as rho times dv. So instead of a mass integral, we'll be integrating over the entire volume. And so our mass moment of inertia becomes rho, mass density, times the integral of r squared dv, integrating over the entire volume. Now, this integral that we just talked about, the integral of rho times r squared dv, we can integrate from the point of view of any coordinate system that we want. So we could have a very tiny object of very tiny mass located a very long distance away from the origin of a coordinate system. So that very tiny object, because it is very, very far away from our coordinates, could have a very large moment of inertia. Okay, and what we typically do is reference the coordinate system to the object, and what we most typically do is reference the moment of inertia to the center of gravity of the object. Okay, and so if we do use a coordinate system located at the center of gravity of the object, where that's the origin, and we use that for our integrals, then we would say I becomes I sub g, or the mass moment of inertia about the center of gravity. Now, what's nice is if we know the mass moment of inertia about the center of gravity, then we can find the moment of inertia about any other axis parallel to the axis through the center of gravity using the parallel axis theorem. So let's talk about that. We know the moment of inertia, the integral was taken about the center of gravity, where that was treated as the origin for the integral. Now we want to know the moment of inertia about this set of axes. And so if we know the distance r, or the distance d is what we'll call it, from the center of gravity to the axis that we want to move it to, and we'll talk about the word parallel in just a second, then the moment of inertia about our new axes is the moment of inertia about the center of gravity plus the total mass of the body times the distance that we're going to move it squared. Now, why is it called the parallel axis? Because our moment of inertia is actually measured about an axis, or a line, in this case that passes through the center of gravity and runs out of the page and into the page. So it runs perpendicular to the plane. So that is our axis for which we were talking about the moment of inertia about an axis. If we then want to move the moment of inertia to the point located by this xy location, these are two axes, but the axis we're talking about for the moment of inertia is the axis perpendicular to the place that we moved it. So this would be a moment of inertia about our z-axis. Then we'd have a moment of inertia about an axis coming straight out of the centroid. Therefore, our old axis coming out of the page through G, our new axis coming out of the page located at the xy coordinates coming out of the page, those two axes are parallel to each other, and the distance between those two parallel axes is the distance d. Therefore, moment of inertia anywhere is moment of inertia about the center of gravity plus mass times the distance squared. Now this does imply something, and that is the smallest conceivable moment of inertia for a body is the moment of inertia through the center of gravity, because moving the axis for the moment of inertia to any other location implies adding a positive number, because that distance is always squared. So the smallest moment of inertia for a body through a axis system is through the center of gravity. We will be using moment of inertia a little bit later in calculations, and we can use the definition of the moment of inertia to calculate it, or we can go to tables to calculate it. But there's another property that is very closely related to moment of inertia, and it's called the radius of gyration. Okay, and the radius of gyration related to moment of inertia is the mass times some quantity k squared, where k is the radius of gyration, m is the mass of the body. Okay, and let's just take a look at what this thing means. There is a particular body that has moment of inertia mr squared. Let that screen settle down for a second. And that body is a ring. If I have a perfect circular ring, thin ring, of radius r, and I place all of the mass of the ring on this line out at a particular radius, then the center of gravity, of course, is located at the center of the ring. And so the moment of inertia of a thin ring of mass m and radius r is mr squared. So what we're basically saying when we talk about the radius of gyration of an object is, what would the object feel like? How would its mass distribution feel if we took all the mass and distributed it as a thin ring? What radius would all of that mass distribute to give us the same feel? Sometimes in problems I will give you the I value. At other times in problems I'll give you the K value, and then you can use the definition of radius of gyration to calculate the I value. At other times, in homework problems in particular, you'll just have to look it up. On a test, I will probably give you the I values or the K values. Okay, let's take a look at the idea of radius of gyration and parallel axis theorem. So find the radius of gyration of a swinging door of mass m and width a. So swinging door is a rectangular plate, and that swinging door would be swinging about an edge. Let's see. Let me look at which. Let me just peek ahead a little bit. Okay. We could have a mass moment of inertia about the edge. We could have mass moment of inertia about an axis parallel to it that passes through the center of gravity. Okay, what we find out from the back of the textbook is for a rectangular plate of mass m, the moment of inertia about the center of gravity is 1/12 m times a squared, and we said that the door has a width of a, so this is quantity a. Okay, and turns out that for moments of inertia about these axes, it doesn't really matter how tall the door is. What matters is the distance a. Now the question is, we have the moment of inertia about this axis. What's the moment of inertia about this axis? And since we're moving away from the center of gravity, we'll say the moment of inertia somewhere else is equal to the moment of inertia through the center of gravity plus the mass times the distance that we're going to move the axis, quantity squared. Looking back at the picture, the door width was A, and we're going to move it from the center to the edge. So we're going to move it a distance A over 2. And so our moment of inertia will be our original moment of inertia, 1/12 ma squared, plus m times a over 2 squared is going to give us a 1/4 ma squared. And isn't it interesting how much the moment of inertia grows when we move it away from the centroid? Okay, it started off as 1/12, and this would be 3/12. So 3 times as big is what we're adding in, so that our final moment of inertia is 1/3 ma squared. Now, taking that moment of inertia about that edge, radius of gyration about that edge would be a k squared. Let's see, going back to our formula, I is equal to mk squared. So k squared is I over m, or we take the square root. So mk squared, 1/3 ma squared, subtract the m's, take the square root, k is equal to a over the square root of 3. For a problem like this, I could give you the k value, or I could give you the I value of the centroid and ask you to move it out to an edge if we wanted the moment of inertia about an edge. Okay, we're not going to have a lot of new equations out of this chapter, but looking at sort of a vector picture of relating forces, moments to various kinds of accelerations, and because we're talking about rigid bodies, we now have, and planar rigid bodies, we have possibility of the acceleration in the x, acceleration in the y, therefore having a total vector acceleration. But in addition, we have the possibility of alpha, and these quantities are mass times acceleration, something that deals with how much mass we have times its linear motion. And the quantity on the right hand side of our equation in this chapter we will be adding is moment of inertia, a measurement of mass distribution times the angular acceleration. So we have both forces and moments equal to mass times acceleration and I alpha. What if we have all of our moments being measured about the center of gravity? Then we can talk about the sum of the vector forces is equal to the mass times the acceleration of the center of gravity, and sum of all our moments that have been measured about the center of gravity. It's very important where we measure our moments. Sum of all our moments measured about the center of gravity is equal to the moment of inertia about the center of gravity times alpha. Excuse me. Let's look at another case. And so we'll have different flavors of the equation that we can use. This would be moments of inertia, moments from our forces measured about an arbitrary point P. So we have these forces acting on the body. Notice some of the forces pass through this point P, and that might be a convenient reason that we want to measure the moments of all the forces about a particular point P, because it eliminates some of those forces, not all of them, but some of the forces from the moment equation. So in this case, F2 does not pass through the point P, so it would contribute to the moment equation, but F1 and F3 produce no moments about P. And so we can still say sum of all forces is equal mass times the acceleration of the center of gravity. Okay, that one's always going to be true. But now that we're no longer taking our moments about point P, about the center of gravity, we can no longer say sum of moments is equal to Ig times alpha, because we're taking our moments somewhere else. We need a correction term. Okay, and this correction term is a row vector cross mass times acceleration. Now this row vector is row, or a radius vector, a position vector, PG, okay, P heading toward G, and notice this row vector showing up in the picture. It is a vector that goes from P and it ends at G, okay. That would be that row vector, and we'll cross that with mass times the acceleration of the center of gravity. Now, is this the simple cross product that I taught you in chapter 16? It absolutely is not. This is a planar vector with two terms in xy. MA is a planar vector with two terms in xy. This is absolutely not the simple cross product I taught you just a few days ago in chapter 16. We actually have to work out this cross product. Okay. Now let's see. Another possibility of the equation. Let's compare these very carefully. We're still going to take our moments about point P, but rather than using IG, we're going to use moments of inertia measured about P. So sum of moments measured about point P is the moment of inertia measured about point P times the alpha of the body times a rho PG cross mass times the acceleration of point P. Okay, and so it's a different point of view. Now, and don't worry too much about these equations. In the end, we're not going to be making use of all of these different flavors. There will be an occasion when these are a little bit easier, and we'll talk about it. But in general, sum of moments about the center of gravity equal IG alpha. Going back to the very first one, you can always use this, okay, and you will get a correct answer. Sometimes using these others might be a touch faster. Now, when this point P that we've been referring to happens to be a fixed point called O, what do we mean by a fixed point? Meaning we are pivoting about a permanent center, or sometimes in the right geometries an instant center. So if this P, this arbitrary point we've been talking about, is not quite so arbitrary, we can still say sum of all the forces is equal mass times the acceleration. But our sum of moments taken about that point P, which is a fixed point, can be written as I about that very same fixed point times alpha. Why is that true, and how is this equation different than this equation? Well, P becomes O, so we've decided our arbitrary point P is a fixed point. We use I of P, which is I of O, but we lose this term. Why do we lose this term? Because the acceleration of point P showing up right here is 0 in this case, where P is a fixed point. Why? Because P is not moving. It is a permanent center. I just noticed my pen is leaving splotches behind, but we're going to go with that anyway. Okay, that really is the end of the lecture. What I want to do is pop over to the computer. Give me just a second to grab the equation sheet, because I probably do have it handy. Let me go to the right place to grab the equation sheet and pop it up. Forgive me, I should have had that open earlier, but it won't take me very long to grab the equation sheet. I'm almost there. Equation sheet, PDF file, there it is. Okay. Oops, I'm sorry. I was thinking I was in a different computer program, and so that you could see the equation sheet the instant I brought it up on the screen, but you can't, and so it'll just take me another moment to print it. Here it comes. Go grab a Coke. It'll take 20 seconds. Please, printer. Here comes the printer. Well, because you can't see it where I dragged it, I'm going to move that out of the way. And what I want is the second page of the equation sheet. Here it is. And let's look at what we've added to the equation sheet. Sorry for the delay. We have added sum of forces equal mass times the acceleration of the center of gravity. Then we have added sum of moments about I alpha. And this equation is true. Okay. First of all, presuming our moment of inertia is constant. It is true when the sum of moments is taken about a fixed point, and when I is then referenced about a fixed point. Okay? Or it's also true when we're referenced about the center of mass. So this could be, we could put a G there and a G there, or we could say sum of moments about a fixed point, O, is equal to O alpha. That G really needs to be next to the I. That's an IG. So moment of inertia taken about the center of gravity, and moments all summed about the center of gravity, or moment of inertia taken about a fixed point and sum of moments taken about that same fixed point. Now, can that fixed point be a temporary fixed point like an instant center? No, in general it can't be, because looking at back at where the equation came from, even if a point is an instant center, we don't know that its acceleration is zero. There are a few places where the acceleration of the instant center happens to be zero, and it deals generally with wheels that are rolling without slipping, those kinds of problems. Generally, the acceleration of the current instant center is also zero, and we'll be able to use this equation. We'll talk about that a little bit later when we face those kinds of problems. This basically ends the technical discussion, and so I'm going to end this video in just a second. Just we'll show you in our notes some of the kind of problems that we have. Some of the problems basically say, are we about to tip? Are we about to do a wheelie because of our accelerations? Is this bottle on a conveyor belt about to tip over? Would be a kind of problem. This wheel rolling down the hill, okay, and rolling without slipping presumably. And we will certainly be dealing with moments of inertia and rotations. Let's see what else we have. Another wheel rolling down a hill, thinking about it a little bit differently. And I will bring in some other example problems as well. I will start these examples in the next video, so we'll end this one.